Alright, recording has started, and alright, let's start with a practice quiz. And couple details before we start. Let me remind you again, group numbers. If there's anybody here today and it's their first day in class, then would you please enter that in the text channel at the center of the screen, and then during a break just kind of check in with me. Here's your group numbers. I'll probably forget to mention this later on. So today we are going to do 6.2, and I'm going to have you check number 32 with your group before class on Wednesday. So anywhere between now and Wednesday, get together with your group, however way you decide, or a portion of your group, and make sure you're all correct. You agree on your answers for number 32. And we're going to start now with a practice quiz. And practice quizzes are, they do not count as real quizzes. You don't even turn them in, but you take them as if it were a real quiz. Don't look at your notes, don't use any assistance. You can use a calculator, that's about it. Alright, number one. I'm going to give you a minute for that. Okay, so 30 seconds more. Alright, the area is equal to an integral from 0 to 2 on the x-axis of the function like this. And then definite integral, we need an antiderivative. We don't put the plus c because instead we evaluate it from 0 to 2. I'm going to put in zeros. Everything's going to zero out, so I'm not going to bother writing that down. Plugging in the 2's, I'm going to get 8/3 plus 2. Now this is what? 2 2/3, so it's going to be 4 2/3. Like this. Alright, so just a brief reminder of techniques for a definite integral and what it represents. It's area under a curve. Okay, let's go to number 2. Let me give you some time for this one. 30 seconds more. And if you don't finish, that's fine. Just get as far as you can. Alright, go ahead and stop. And this needs a U substitution. Okay, now what I'm seeing up here, I could pull that 2 here out front, or I could just leave it. All that stuff, I want to get that right here. So if I multiply both sides by dx, I get du is 12x squared dx. Divide both sides by 6, so I match 2x squared. 1/6 du. So now this is exactly matching the leftovers up here. So now I can make this integral. Now these are x equals, and I'm going to rewrite the whole thing without using any x's. So this 2x squared dx is going to get replaced by 1/6 du. The square root of 1 plus 4x cubed is going to be rewritten as, so 1 plus 4x cubed is u. Instead of putting it as square root in the denominator, I'm going to put, for the denominator part, put a negative exponent. For the, there's really an unwritten 2 for square root. And there's an unwritten 1 to the first power. This number comes underneath that. So it's x u to the negative 1/2. And then 1/6 du. And then I'm going to change my limits. When x is equal to 0, plug it in here and u will be 1. When x is equal to 2, plug it in and I'm going to get 8 times 4 is 32 plus 1 is 33. So then I'm going to get 1/6 u to the, add 1 to the exponent, so it's u to the 1/2 over 1/2, which is the same as multiplying by 2 over 1. And then I'll leave the constants up front, evaluate this from 1 to 33, and this reduces to 1/3, and then I get the square root of 33 minus the square root of 1 is 1. So I'll just have minus 1 right here. And this represents the area under the curve of this big function from 0 to 2.
Mr. Shankin,
Yes.
I have a question. Since it's negative 1/2, would you multiply by negative 2 instead?
We add 1 to the exponent.
Okay.
So thanks for pointing that out. I'm using the idea of u to the integral of u to the nth du is u to the n plus 1 over n plus 1 plus a constant. That's the rule. All right, so give me some feedback on these two problems. If everybody could type something in, if one of them was difficult, one was easy. If you really struggled on one, need more practice on one, don't need any more practice, good to go. Just let me know where you're at with these two problems. Okay, a couple questions on the du dx with number 2. So let's go over number 2 again. So, all right, one of the abstract steps in number 2 was figuring out what your u is going to be. And in general, you need, if you have functions of x and you have 2 of them, you need the one that's 1 degree higher to be your u. And then your other one will be your du. So we set the u to be 1 plus 4x cubed. I'm going to take the du dx, the derivative of that is 0. This is just 12x squared. Multiply both sides by dx, 12x squared dx. Now, another way I could have done this is I could have brought this 2 out front and then just solved this thing for x squared dx. And then I would have divided both sides by 12. And then I would have had 2/12, which would have been the same as 1/6. But that's how we wind up getting this 1/6 out here. Alright, so let's go on to number... Yes?
Maybe I think they're asking why you got 12x squared, and I see how you got it, but maybe they don't understand.
How we got the 12x squared from the 4x cubed?
Yeah. Yes.
Okay, that's just this rule, which is d dx of x to the n is nx to the n minus 1, which is the basic power rule. Okay. And let's go to, thank you, Kylie. Number 3. Find the area of the shaded region. Now this goes through the origin. Kind of my picture doesn't look that great. Imagine it does go through the origin. It's y equals 3x. And find the area of the shaded region using geometry and using calculus. I'll give you a little more time on this because this is kind of challenging. Okay, about a minute more. Just get as far as you can.
Professor, would you be able to go back just for a second so I can copy the other rule? Just really quick.
That's the one you want to see? Number 2?
Yeah. Thank you.
I'll put it there for just a little bit.
Okay, I'm good.
You're good? Okay. Alright, let me have you stop on this one. Alright, so I'm going to redraw this picture from 1 to 3 and then go up. This one goes to a height of 1/3. And this goes up to a height of 3, no, of 1, and so by geometry you can make a rectangle down here and a triangle up here, but that kind of takes a while. A very quick way to do it is find the average height if it's a line. So the height on one end, so average height one-third plus 1, add the two numbers, divide by 2 to find their average. So that's 4/3 times 1/2, because you flip this one, and then you get 2/3. So halfway in between is 2/3. So the area is the width times the average height, which is 2 times 2/3, which is 4/3. Alright, so we can come up with that. Now we are asked to do it again with calculus, and when we do it with calculus, we run into a difficulty. Calculus will give us the area underneath this curve, and it would only give us this area here. It wouldn't give us the area over to the y-axis. But then again, it will. This is one way that we could interpret an integral, is area under a curve. But let's look at this again. Suppose we did this, instead of y equals 3x, let's solve for x. Divide both sides by 3, x equals 1/3 y. Okay, now that is a valid equation of this red line, just as valid as y equals 3x. All right. Now, if I took this integral from y equals to y equals, and I put a dy over here, then what I need in here is, well, you see how we set up the other, normally when we set up integrals, up here we put the right hand side, because when we're doing dx we need it solved for y, and then we have a function of x to put in instead of the y. This is going to work just the opposite. We're going to do solve for x, x equals 1/3 y, and that is going to go in for the x right here, 1/3 y, dy, and then the y goes from 1 to 3. Now, if you're freaking out a little bit, saying, how in the world can you do this? This is not what the... Remember, when we have an integral like this, we have only chosen this representation because we chose to put the x-axis on the horizontal and the y to be on the vertical. We could have decided, well, x should be on the vertical and y should be on the horizontal. I mean, this representation is just a convention. And when we use that convention, it has this representation. But this integral doesn't know that there's this picture associated with it. And so we come over to here, we can do this stuff. If the y was down here and the x was up here, then we would wind up having a 1/3, and it would be just like we're used to. But we can also just visualize it as, when the x's, when we're doing with the x's, we were going up from the bottom. From the bottom up to the top of my graph. All the lines were kind of coming up like this. All right. We go from x equals 0 to 2 up until we get to the graph. When we do it in the other manner, we go from 1 to 3, and we start on the x-axis, start on the y-axis, similar to the way we were starting on the x-axis before. We go to the right in the positive direction until we get to our function. And we will wind up getting the area over here. So, now, you might say, that's just theory. Well, let's test out our theory. Well, let's do this integral, and I'm going to have 1/3. I need an antiderivative of y, which is y squared over 2. Evaluated from 1 to 3. I get 1/6. When I put this, I get 9 minus 1. I'm going to get 8/6, which is 4/3. Exactly the same answer that I got before. This gives us a new tool. We can find areas under curves down to the x-axis, but we can also find areas to the right of the y-axis coming out to the function. And if it was to the left of the y-axis, we'd just get a negative area. Just like if we were underneath the x-axis, we would get a negative area for an integral. All right. Number 3 was a bit complex. Give me some feedback. Everybody give me some feedback, both on the geometry one and the calculus one. Where are you at with these? Do you understand it? You're very uncomfortable with it? Where are you at? Okay, so it's looking like you're getting it, but you're not used to it. Maybe like some more practice with it. And I can give you some more practice in the future. Let's go to number 4. Distance traveled and displacement. Suppose an object is moving along a line with velocity in feet per second. And there's the equation. T is measured in second. Graph the velocity function. Determine when the motion is in the positive direction, when it's negative. So let's have everybody do just part A. I'll give you a little time for that. Now if you finish part A, you can go on to the other parts as well, but I'll go over part A in about 30 seconds here. Okay, let me have you stop and so t and v of t, and we need to go to 6. And when t is 0, we're going to get 6, so we need to go up to a height of 6. Okay, and this is a straight line coming from here. And when t is, it's going to have slope -2. So when t is 2, no, when t is 3, I'm going to have 0. When t is 2, I'm going to be at 6. When t is 6, I'm going to get -6. Alright, so this is a symmetric shape like this. Alright, so when it's going in the positive direction is when t is between 0 and 3. Because as long as the velocity is a positive number, above the x-axis, positive number, then you have positive velocity. That's going in a positive direction. When is it going in the negative direction? Whenever v of t is negative, when it's, so that's t between 3 and 6. Now at 6 it's still going in the negative direction. At 3 itself, so actually at 0 itself is still in the positive direction. Okay. 3 is when it's transitioning. It's neither in the positive nor in the negative direction. Okay, so that's my answer for A. Okay, now go on to B, find the displacement of the object. If you haven't already done so, let me give you another minute. And if you can find the displacement without calculus, fine. But also do it with calculus because you need the practice. So when we, on a problem on a test, I'd probably give you something that you wouldn't be able to find unless you could use calculus to get it. So let's go part B. And the displacement. In calculus, the formula for displacement is the integral from the first time to the second time of the velocity and why is this? Well, again, remember when we did like the geometry one over here, we found like the average height. You might find the area under the curve by finding the average velocity. Find the average velocity times the amount of time. If I averaged 5 miles an hour for 3 hours, I was going to go 15 miles. That's distance times time. So this one is going to be 0 to 6 of the velocity function. Oops. and this is equal to antiderivative of 6 is 6t, antiderivative of minus 2t is minus t squared, evaluated from 0 to 6. When I put zeros in, everything's going to zero out, so I won't even write that down. I'm going to get 36 minus 36, which is 0. So the displacement is 0, and that makes perfect sense because you spent equal amount of time going in the positive direction and going in the negative direction. And then part C, find the distance traveled by the object. Let me give you a minute. If you haven't already done the distance traveled, do that now. Okay, 15 seconds more. Alright, let's go for the distance traveled. C, integral from the first time to the second time of the absolute value of the velocity. And distance traveled just means as if you're going in the positive direction the whole time. And now when we do this though, 0 to 6 and the absolute value of 6 minus 2t, this is usually too awkward to integrate. We usually don't like absolute value stuff, so we get rid of it. We look at the geometry of the problem and we say, it would just take this line that's going underneath the y-axis and it would put it above the y-axis. And the area under the curve under both halves is going to be the same. So the way we typically do this kind of integral is look at the geometry and say, oh, that's double the integral from 0 to 3. And when you're just going from 0 to 3, you don't need absolute value anymore. Okay. If the two shapes weren't symmetric, you'd still split it up. You'd go 0 to 3 and then 3 to 6. But then you'd put an extra negative sign in front of the function that was from 3 to 6. Okay. So then this becomes 2. We find the antiderivative, 6t. The antiderivative of t squared is t minus t squared from 0 to 3, which is 2. When I plug in 0, everything zeroes out. I won't bother writing that. 2 times 18 minus 9, which is 2 times 9, which is 18. So this makes sense as well. Distance traveled is 18 watts, feet. Let's put our units in here, 18 feet. If we use the idea of the average velocity was 0 because equal amount time positive and negative, and 0 times 6 seconds was 0. If we did the average velocity from 0 to 3, it would have been 3 feet per second, halfway height. So the average velocity of the whole thing was 3 feet per second times a total time of 6 seconds gives a total distance of 18 feet traveled.
Mr. Shankin,
Yes.
can you please explain why the interval changed from 0 to 3 rather than 0 to 6?
Okay, it's because of this absolute value. We have a hard time integrating with absolute value. We got to get rid of it. And so there's two choices to get rid of it. Make the integral go from 0 to 3 and then 3 to 6. And then when it's negative, you'd put an extra negative sign to turn that into positive. Or if you see that it's totally symmetric on both sides, which it is in this case, because of that symmetry, this is going to have exactly the same area as this half over here. And so we then say that's from 0 to 3, but just double it. All right. Any more questions with regard to this? All right. Give me feedback on this. Could you do these on your own without, could you handle one part of it maybe without the calculus and you could kind of intuit the answer, but not so comfortable with the calculus? Or tell me where you're at with these types of problems. Seems generally that you want more practice with those. It's good feedback. All right. That finishes the practice quiz. So now, questions on homework. And just go ahead and use your microphone. And if I think we've got Nehemiah with without a microphone, so you could also put it in into the text part. Okay. All right. So number 9. All right. So number 9, you're right. It doesn't give a function, and what it wants you to do is use areas. So let me pull up number 9. Gotta get to it here. Should have pulled this up earlier. I forgot to do that today. It's hard for me to get back into the rhythm of everything I need to do sometimes. I'll get it down in a little bit. My math lab is being slow in coming up. Let's see if there's anything else to do while that's... Yes, I am recording. All right, tell you what. If it's not up yet, it's not. What I'm going to do is let's go to 6.2, and I'll do 6.2 for a little bit until we take a break. And then during the break, I'll put up the other problems from my method. Alright, so now this is not moving around right now. I may have to close this out and redo one note. Hang on. Okay, here we go. So 6.2, regions between curves, area between curves. And example number 1. From x equals 0 to x equals 3, we will find the area between f of x equals 3x and f of x and g of x equals x squared. Okay, so here's x squared, part of a parabola, and here is y equals 3x, a straight line. They intersect at 0, 0 and at 3, 9. And we're trying to find this area between these two. Now, together we'll estimate this area. And what I mean there is, area is, if this was 1, height of 1, height of 2, then a square unit would be like this. And you'd have all these square units. And you'd kind of look in here and say, all right, how many of these square units could fit inside this shape? So I'm going to guess that my area is definitely some positive number. And how many of these squares in here? I'm going to say maybe, 6. I'm just going to guess. And I might be way off, but it's not going to be 600, and it's not going to be negative, and so on. So if I just get something in the ballpark, so that when I do some calculus, if I get something like 600 or a negative area, I'll know I'm wrong. So I always do some kind of estimate beforehand to orient me, so that when I do my calculations, I can see if they're reasonable. Okay. Now, we're going to do this in stages. Part B. Find the area under F for x between 0 and 3. This part I think I can handle. So, this one is F. I should have probably put this as, there's F. And this one over here is G. So, the area under F from 0 to 3 is you just put the F function. And then the antiderivative of 3x is 3x squared over 2. I like to keep all my constants factored out. And then I get 3 halves. When I plug in the 0, it's just going to zero things out. All I'm going to get is 9. So I get 27 halves, which is 13.5. Okay, so 13.5 square units is, now that's a lot bigger than 6, because that's just the area between the curves. 13.5 is the area underneath F, all the way, all the area underneath it. So it's that whole triangle. All right. Next, we're going to find the area under G. And the area here, well, the G curve is x squared dx. So that's going to be x cubed over 3 from 0 to 3. And then when I plug in 3, I'm going to get, well, I plug in 0, it'll disappear. And so that's going to give me 27. And 1/3 of that is 9. Okay, we're going step by step. Okay, now I want you to do part D and E on your own. And I'm going to give you a little bit of time after you do D and E on your own. Put them into, put your answers in with your group, and then I'm going to call on a group. So, don't enter your answers, type up your answers now. Once you get them, the area between F and G, you can type them in right away, but don't hit enter yet, because I don't want other people just kind of seeing what everybody else put and then typing in their answer. So, on my cue, I'll have everybody hit enter to enter their answers into their group channel a little bit later, in a minute or two. This shouldn't be answer, this should be area. Okay, go ahead and hit enter and discuss this in your groups. Okay, 30 seconds more. Okay, let me have you stop. All right, group leaders. Let me run over the responsibility of group leaders again. What I want you to do each day is go to your group and enter in who is the spokesman for that day to remind everybody. So there's no, like, I call on group 3 and you don't take a minute trying to figure out who's the spokesman for today. Group leader does that first thing each day. We rotate alphabetical order by first name. And then if I call on group 3 and the spokesman for the day doesn't respond in a little while, maybe they've had to step away or their computer has crashed or whatever, then the group leader jumps in and says, so we've got a backup for each group, so we can kind of move quickly. also, it might happen that people get lost during the lecture, and if you get lost, go into your group channel and type in "I'm lost." And if the group leader agrees or sees two people that say they're lost, then the group leader needs to interrupt me. And anybody, I make lots of mistakes. I have a really hard time saying one thing and writing something different, and so what I say bleeds into what I write, and that makes and plus I tend to be error prone as well. So interrupt me when I make mistakes. So now, let me ask group number 6. What do you have for part D? Oh, and when you first talk, if you say your name first, your first name.
Hey, this is Ethan. I'm on a phone call right now, so I have to pass this one. Sorry about that.
Okay, no problem. Let me switch over then to group 2. Group 2, what do you got for D?
Hi, this is Herman
Okay.
from Group 2. For E, our consensus
How about
is
D?
D.
Mm-hmm.
Well, we didn't really have an answer, but I thought the integral from 0 to 3 of x squared minus 3x.
All right, let me write this down. 0 to 3 x squared minus 3x. Okay.
Oh, I'm sorry, that's for E. Our answer for D was 4.5.
4.5. And you got that by just doing what?
Yeah, we subtracted 9. Well,
Yeah,
I did
that's
from
right.
13.5.
All right, and that makes total sense looking at the picture. You have this area underneath, which we'll shade in red. It gives you too much area. So what do? We take off the area underneath G. It cancels that area out, and it only leaves you with the area between the two curves. So that's the answer. And then now E, keep going, Herman.
For E, we were not sure, but I figured maybe the equation I told you before.
Yeah, this one, and then like this, and put a dx
Yeah.
on the outside of it. All right, this is really close, but it's got something that's wrong. And what's wrong is, let's look at which one is the upper function. The one that's going to give you too much area is the 3x. That's got to go first. And then the one you subtract off is this. And that's the way we did it. We did it 13.5 minus 9. So you're on the right track. But the order is really important here. So if we get the area this way, now you get the same answer if you had it backwards, but you would get the wrong sign. And we want it to be a positive answer, like this. All right, now, what property are we using? Herman?
I'm not sure.
Okay, this is kind of a tricky question. I'm going to open this up to anybody. Anybody, what property?
The difference property?
That's right. And how do I write the difference property?
We take the integral of the first one minus the integral of the second.
Integral of f of x dx is the integral of g of x dx equals, and what goes on the right-hand side?
Should be f of x minus gx.
Dx. That's right. It's the integral, or the difference of two integrals is the same as the integral of the difference of the two functions. So conceptually, we probably want to think of it this way. But because of this property, it'll go quicker if we just write it like this. And we don't have to do two separate integrals. We'll just get our integral like this. All right, now this function, when you subtract two together, is actually pretty tricky. F of x minus g of x. Let me just show you. Let me come back to this picture. If I was, this is my x, this is my y, here's my f, here's my g. If I want to draw a picture of f minus g, I got to go point by point. At 0, 0 minus 0 is 0. At 1, f is about, I don't know, about a half a unit higher than the g value. So it's going to be about 1/2. When x is 2, it's about, more than a whole unit, maybe 2 or 3 units, that the f is higher than the g. So you're way up here, And then at 3, they're both back at the same height. Here, the f minus g graph might be something like this. And then you're finding out the area of the f minus g, but you don't need to visualize this. That's the visualization of this, but we just visualize it this way. We use the abstract property, though, to write it this way so that the calculation goes really, really fast. And when we do the calculation, we need an antiderivative of 3x, which is 3 times x squared over 2. When I have more than one, I'll just keep the constants in there. Minus an antiderivative here is minus x cubed over 3, evaluated from 0 to 3. When I put 0 in, it's going to zero everything out, so I'm just going to put the 3 in. I'm going to get 27 halves minus 27 thirds, which is 9, which is 13.5 minus 9, which is 4.5. We get the same answer. Goes very quickly. All right. We are going to take a break now, and afterwards we're going to generalize some things out of this. But we've gone an hour, so we will start again at 6:45. If anybody needs to talk to me, you can hang and I can chat with you for a little bit. Otherwise, I'll take a break as well. I'll set up also some stuff for questions on homework.
I have some question. Can you hear me?
Yes, I can hear you.
For the spot checking, how many percent of homework we should do?
75%. Okay, when I do the spot check, I don't check any problems for correctness. I'm just seeing, do you have at least 75% of them done? By the turn-in date, then I check for correctness. Yeah.
Okay, thank you.
You're welcome. Any other questions? All right, welcome back. Let's start up again. And so, before generalizing our findings, well, actually, let me finish this up. We'll generalize our findings, and then I'll go to answer a homework question. All right, so we got this result, and we see that we can use this property to write something really efficiently and get the result for the area between two curves. This works remarkably even when, let's say, one of the curves is below the x-axis. Let's insert a little more space here. If we have one of the curves is f, the other curve is g, and we're going between a and b. If I find the integral from a to b of f of x minus g of x dx, I'm going to get this area under f. It's the same as the integral under f. I'm going to get this as a positive area. Normally I would get this down here as a negative area when I would do this, but I have an extra negative sign that's going to cancel out the negative that I would get over here, and so it'll give me this as a positive area again, and it'll be correct. It will still work even if both curves are below the x. Let me put this x-axis up here. If here's my f, here's my g. And we're trying to find between a and b the area between these two curves. Alright, now, which order would I put them in? This area, would I do it f minus g or g minus f? Well, you want to have the upper curve minus the lower curve. If you get it backwards, the lower curve minus the upper curve, you will get the wrong sign. So it doesn't matter where they're positioned, even here. If you do, as long as you do the upper curve minus the lower curve. And when you take the integral of the f, what you're going to get is this. And let me make sure, double checking that I'm muted. We're going to get this as a negative area. And then we're going to get, when you do the g, f minus the g, the g is going to be a negative area, but it'll have an extra negative sign, so it'll turn all this into a positive area. So this will be positive. It'll also give you this area up here, but this area up here will wind up canceling with that other negative, and it'll just give you a positive area between the two curves. So it works. And it also, we can go area between two curves, like we saw in the practice quiz, if we're looking along the y-axis. So if I have two functions, one here and the other here, and I want the area between them this way, I can get that area between the two curves. But I have to, this time, it's the rightmost has to come first, and then the leftmost. Area will be, it's same thing as before, but not upper lower now. It's rightmost, leftmost. A to B. It's from A to B. The right minus the left dx. And then you might ask the question, well, hey, what if, and I'm going to need a little more space. What if there's not a clear upper and lower? Suppose we have from A to B, suppose F is the upper for a while, G is the lower, but then after a while G is the higher one. Then how do you write the area between the two curves? Now, area between the two curves does mean you want everything to be considered positive. You want to get all this area between them as a positive number. So, the only way to do this, well, there might be more than one way, but one way to do it is you create this point where they change, where they're equal in value. So the area between is the integral from A to C, where we're going to do the upper minus the lower, f minus g dx, plus the area from C to B. Now the upper is g minus f dx. And that would give you the area between these two curves. Alright, so that finished up the generalization of things, and I want to switch gears now. Before I go out of this, any questions or comments on this? Alright, hearing none, we're going to go up to problem number 9. I'll do one of these problems that was listed for me to do, and then I'll go back to the lecture and we'll kind of go back and forth. So, the figures show velocity functions for motion along a line. Assume the motion begins with an initial position S0 equals 0. Determine the following. Alright, the displacement between t equals 0 and t equals 5. So, from 0 to 5, what were we doing? We were going in the positive direction for the first 2 seconds because we had positive velocity. Then, we were going in the negative direction for a little more than a second. And then we were going back to the positive direction. There's going to be a little bit of backtracking in between 2 seconds and about 3.3 seconds. But other than that, we're going in the positive direction. Now the displacement is area under a curve. The displacement is, if all you memorized was the displacement equals the integral from a to b of v of t dt, you might be a little stuck here. If you had understood that also this area, this integral represents an area under a curve, as long as it's a velocity curve, and this is a velocity curve. So we can get the displacement. Let me get the displacements for, now if it's straight line segments, I can look at it by average velocity. In the first 2 seconds, my average velocity, well, because the average height is between 0 and 2, so the average height was 1. So my average velocity was 1 for the first 2 seconds. So this is a displacement of 2 times 1, which is 2. Now, in the next, now you're not going to get an exact answer here because we don't have a real function. They didn't tell us what's the equation of these things. We could probably figure it out, but estimate is just fine here. Suppose I went, all right, so now from 1 to, let's say, 1.3, 2 to 3.3. So the width of this is 1.3 times average velocity. And so the width is 1.3 seconds. And my average velocity during that time, well, let me just estimate it. It goes down to a little bit more, maybe about -1, and then back up. Okay, and so my average velocity during that time, half of my time is spent below 1/2, half of it is spent above 1/2. It's about 1/2. 1/2, and unit, it didn't say what the units were. It did say the time was seconds. No, it didn't even say seconds. Alright, so let's get rid of the second. If it was seconds, and then it would be units per second here. And then half of 1.3 is 0.65. And that's negative, because my velocity is negative, so I'm getting negative. So this is negative 0.65 here. And then this last one is positive once again, and it's about 1 2/3 of a second. So my width would be about 1.7 seconds. And my average height, it goes up to a height of 2, back down to a height of 1. Average height is about 1. So this would be 1.7. So add them all up together, and that's going to be my displacement. And let me pull up my calculator real quick. Hold on, I can do this in my head. This is going to be 2.05 plus 1.7 is going to be 3.75. Okay. And then the distance traveled. The only difference in this is you're going to change this negative 0.65 to a positive 0.65, because instead of backtracking, it's still more distance. Like if you're, figuring out how much gas you were going to be using, you'd want distance traveled rather than just displacement. And then the position at t = 5. Alright, well, the position at t = 5, well, it said we started out at 0. My displacement was 3.75, so this would be 3.75 again. The displacement tells me how much did I move. I moved positive 3.75. And then part D, a piecewise function for S of t. So S of t is how far we're moving, our position. And my velocity is, alright, by the time I've moved to, it's got a slope of -1 over here. Alright, so my velocity is 2, let's say it was meters per second when I started, but it's coming down and it's, all right, now with this one, I'm going to jump back to 6.1 velocity and net change. When we were in 6.1, so I'm clicking this one, we ran out of time right at the end of class. I didn't get to this last part. Right here, two equivalent formulas. It says two ways to get the position function from velocity function. And this was also in the textbook, so you could have read about this. So one way to do this is the position function is just the antiderivative of the velocity function. And it says, note, you'll get an arbitrary constant in your answer. All right, now this could kind of help us with this problem that we were just doing, but we would have to see this as, since we don't have an actual function here, we kind of have to see it as area under curves, and then that would be a little bit of a difficulty, because how do I get this as a really a function? And then S of t, the other one is, this one, by the way, would give us an arbitrary constant, but the initial condition, S of 0 equals 0, would tell us what the arbitrary constant was. This next one, another way to get it is you take the integral from 0 to t of v of x dx. Now this looks strange. How come this isn't an x up here? Remember, when you take an integral of anything, the x here and the x here, v of x dx, goes away. But you evaluate it at these 2 points, and so this integral is going to wind up giving us a function of t. And what it is to actually to get that integral, you need an antiderivative. What's an antiderivative of v of x? Well, it's s of x. And then where do you evaluate it? From x equals 0 to x equals t. But when you do this, when you substitute t in, you get s of x, s of t. Substitute 0 in it, you get minus s of 0. Now that's why this gives you the displacement here. It's your final position minus your initial position. But if you were trying to find a function s of t in general, you'd need to cancel out this s of 0, minus s of 0. And that's why you need this other positive s of 0 right there. All right, so let's come back. Oops, went to the wrong thing. To here. Oh yeah, this is what I'm supposed to come back to regions between curves. Right, so the s of t. All right. One way to do this is to estimate what these. Now we can actually, well, I know 2 points on this. I can get the equation of this line right here. This line is y equals, has a y-intercept of 2, slope of -1, negative x plus 2. So that's my velocity function. V of t is equal to negative t plus 2 if t is between 0 and 1, 2, 3. And then I can integrate. If I integrate, stick a dt in there, this is going to give me the integral of the velocity is the position. And then negative t squared over 2 plus 2t. But this is only true in this range, t between 0 and 3. And now we would get potentially a plus c when you do this integral. But they told us s of 0 is equal to 0. So when you plug in 0 for t, you got to get 0 for s, so that tells you that the c is 0. Now, we could do a similar thing. So here is then part of the piecewise function for s of t. You could do a similar thing for this one. You'd have to say, all right, one point on this curve is 1, 2, 3 over, negative 1 down. Another point is 1, 2, 3, 4 over, and 2 up. And then find the slope, find the equation of that line, take the antiderivative, and so on. So that's the path of getting this full answer. And the final full answer for s of t has got to be, like this. And the first part we just did, negative t squared over 2 plus 2t. T squared plus 2t. If t is between 0 and 3, and then you're going to have something else for t between 3 and 4. And then something else for t between 4 and 5. And I'll leave the other parts to you all. All right. Any questions or comments before I move on? All right, let's keep going. Now we're back to example 2. Find the area between y equals x, 4x plus y squared equals 12. It will be helpful to visualize this. Graph both equations on the same grid. And this sounds like an easy task, but you may have trouble with it. So let me give you a minute with this, and then I'll go over the answer. So let's graph those two. All right, graphing y equals x is no problem. Graphing this one is a bit tricky. It would be much easier if it was y and x squared. If that was the case, it's a familiar parabola, you know how to graph those. When the y is squared and the x is to the first power, what that does is it sends it sideways. It's either off to the right or off to the left. And if you solve this thing for x, divide by 4, this. We can see with the same kind of analysis we use for parabolas that go up and down, we can see that this term right here is always negative. Because y squared is always positive, so when you multiply that by negative 1/4, it's always negative or 0. Okay. So the largest that x can ever be is 3. And that occurs when y is 0. If y is anything else but 0, this is going to be negative and it'll make x smaller. Okay? So that tells me that when y is 0, x is 3. Let's go over here. X is 3. 1, 2, 3. That's 1 point on this. And the y, whether it's positive or negative, makes no difference. It's going to give you the same x value. So when the y is, let's say, 1, or the y is negative 1, you're going to be subtracting 1/4 from the x, and so it'll be a little bit smaller. So, here's 1. Up here or down here. So what you're seeing is you're going to get this parabola. It goes to the left because you can get x to be super large negative by choosing y to be super big height. But you can never get x be bigger than 3. So this is some parabola like this. Alright, now I'm going to need to go further on my graph. I didn't do that right. Okay, so this comes way over here. This is as far left it'll let me go. And these two are going to intersect down here. And we're finding the area between these two curves. Okay. Now, any questions with this? Okay. Next part. Graph both equations on the same grid. Oh, next part. Using algebra, find the intersection points. All right. Those are the two equations. Find where this point is and the other point by using algebra. So, let me give you a minute to work on your own. And then I'll have you consult with your group. Not for a minute. All right, consult in your Discord group. And I'm going to choose a group in a minute. Group 3. You can always say pass, but what did you get and how did you go about it to find the intersection points with algebra? Anybody here from Group 3?
We would say pass on this.
Okay, all right. Let me jump to Group 7. Group 7, any ideas?
We thought this is Matthew, and we thought that it intersected at y equals 2.
At y equals 2, and how'd you get that?
So if you just set the two equations equal to each other and solve them algebraically.
How do you set the two equations equal to each other?
Well, first you have to make sure they're in the same form, so that they're both in the x form, and then you just, so for this one to be negative 1/4 y squared plus 3 equals 2.
Gotcha. So you used this equation over here where x equals negative 1/4 y squared plus 3, and this one x is equal to y. Since it's the same x, they got to be also equal to each other, and that gives you that one y equals this x, this equation right over here. So this is going to be the equation y equals negative 1/4 y squared plus 3. All right, now, when you have still Group 7, and what's your name?
Matthew.
Matthew. When you have two equations that you're trying to solve together, what do we call that? Do you remember?
I don't think so.
Okay, it's called a system of equations.
Oh, that's right.
Okay, and there are two algebraic methods for solving systems of equations. Do you remember either one of those? The names of those methods.
Like, I know how to do it, but I don't know like what you would call
I think
them.
that's very, very typical. A lot of students know how to do it like you did. You set x equal and x equal, but you forget the names. All right, the names of those two methods are called substitution and elimination. And when you set x equal this one and x equal this one, then you're kind of like what you're doing is substituting. When you see this equation right here, whenever you see the x, well, let's substitute it with y. And then we have this right here. We could also do elimination. And that means we could like take the second equation and multiply y equals x and multiply both sides by negative 1. And then you put negative x equals negative y, and then add the two equations together, and the x's would cancel out, and we'd wind up getting the same equation in the end, either way. So what we're doing here is called systems of equations, and we're using either substitution or elimination. All right, and then we have to solve this equation. Now, this equation to solve is not a simple one. We're going to, and it's what we call a quadratic equation. So, to solve a quadratic equation, you get everything over to one side and set it equal to 0, and then you factor it, or if it doesn't factor, use a quadratic formula. So what I'm going to do is move everything to the left-hand side, and I'm going to get 1/4 y squared plus y. I'll move the 3 over, minus 3 equals 0. Now, I don't like to have a fraction, so I can easily get rid of that. Multiply both sides by 4. And then I'm going to get y squared plus 4y minus 12 equals 0. Alright, and then this equation, we're going to factor it. y equals 0. And then these two things that I put down in the second term of each parenthesis have to multiply together to give me a negative. So two things multiplying to be a negative, the only way that can happen is if one's positive and the other is negative. And then I need two numbers that multiply together to be 12, or actually, yeah, multiply to be 12, and when I subtract them, I get 4, and that would be 6 and 2. And that will give me the correct middle term right here. And then when I solve this, I'm going to get two solutions. Y plus 6 will be 0 when y is equal to negative 6. Y minus 2 will be 0 when y is 2. So, Matthew, when you said y is 2, you were right on track. That's one of the solutions. The other one is when y is negative 6. All right, now, the x and the y, we know from this equation, they're equal to each other. So the 2 points are going to be negative 6, negative 6, and 2, 2. They're both on the line y equals x, so they had to have the same x coordinate as y coordinates. All right, so find the intersection points. We got them here and here. Now, the next thing is we're going to find the area between the curves. The area between the curves, well, that's complicated because one of these is part of a parabola. So there's no real way to get it unless we use calculus. So set up an integral that is the area between these two curves. And let me give you a minute to work on that individually. Okay, somebody's got their microphone unmuted. So there's a Jay possibly, I think. Maybe Jay is using the same thing that Kylie is using, which is press to type. All right. Maybe the issue's resolved. Okay, go ahead and consult in your groups now with this. What were you doing? Even if you're not totally able to get it, if you can kind of have a strategy that makes sense, that will be interesting, and I'll call on a group in a minute. All right, group 6. How do we go about finding the area between the two curves?
I can answer that.
Okay.
It would be the top minus bottom equation, or the integral of the top line minus the bottom line, with the limits set to what we just found. When so it'd be 0 to where the lines intersect.
Okay, so this would be the area is equal to the integral from where to where? What number to what number?
It would be 0 to is that 6?
This point over here
See
is
what-
-6, -6. This point is 2, 2. And this way over here is 3, 2.
You would plug in the point for when x is equal to 2, what y is.
The y would also be 2.
Oh, okay.
So from 0 to 2,
Yep.
okay, 0 to 2 of what function comes first?
So that would be, let's see, how did I write it? That would be the y, sorry, I rewrote it. But it would be the equation that was originally 4x plus y squared is equal to 12.
Okay, that one, when you've solved it for y, maybe?
Yes, and then you would subtract the other equation, and then you would take it in terms of dy.
So that would be y squared is equal to 12 minus 4x. So y is equal to plus or minus the square root, 12 minus 4x. And, all right. So we'd take one of those and we'd put it in over here and then subtract the other one, which would be the x over here. All right. You are, and what's your name?
Tristan.
Tristan. Thank you, Tristan, for pushing us in the right direction here. It's this integral. I think it might make sense to go not just from 0 to 2, but to go from -6 to 2. From way over here on the left to, and we get these two functions subtracted inside this parentheses. Now, this is almost correct, but it's got a problem. The problem is this. The upper function is the green curve, but only till 2. Then from -6 to 2, it would wind up, and this thing that you would give us would be the area under the curve, under the green curve, between the green curve and the gray curve, up to here. But we want the area all the way up to here as well.
Okay, so you would just,
that area, but you'd be missing this area. Go ahead, Tristan.
okay, so then you would add another integral and then reverse the subtraction of the equations.
Actually, you could add another integral, but it wouldn't reverse the subtraction because way over to the right, notice the green curve isn't involved anymore. It would be, one of these would be the positive and the other would be the negative of this really difficult thing. And this thing with the square root is kind of difficult to integrate as well. So we would need 2 integrals to do this. And one of the integrals is going to be kind of messy over here. So what we're going to do, so I remove that line there, is we're going to say, hey, there's an easier way to get this integral. We can get it all in one integral. We can get this area in one integral, but we got to look at it in a different way. Because there's no consistent upper and lower function, after a while it's the same function that's the upper and the lower. And it's not for the entire integral that there's one that's upper and one that's lower. Because of that, we ask, is there a rightmost and a leftmost function? And there is. The parabola is the rightmost function the whole time. And the line is the leftmost function the whole time. So instead of doing this one, because there is not a consistent upper and lower and lower function. Instead of that, we're going to go this way. Area is, we're going to do everything in terms of y. We're going to put a dy over here. And this is like what we did in the practice quiz, is we set up integral to get areas from something out to the right back to the y-axis. And this is what we're going to do here, is we're going to take, as long as we take the rightmost function minus the leftmost function. So we need, and I'm going to put y equals. What are the heights that we're going to go from? The smallest height is -6. The highest height is 2. So -6 to 2. Then we need the rightmost. And then the other function has got to be the leftmost. And there is one function that is consistently the rightmost, and there's one that's consistently the leftmost. So although we could do it up and down, it's way more complicated. It's going to take 2 integrals. It's much easier if we consider rightmost and leftmost. Okay, the rightmost function is this one. 4x plus y squared equals 12. Now, there's 2 ways we've solved it. We've solved it for y, and we've solved it for x. Which one of those 2 do we want to use to plug it into here, the rightmost? Well, if we were going up and down, uppermost minus the lowermost, we want y equals. That's the one we would use if it was going uppermost one. And when we're going rightmost to leftmost, we want x equals. And so this is what we're going to use right here. The -1/4 y squared plus 3 is the leftmost, or is the rightmost function. -1/4 y squared plus 3. Oops. Minus, and then, now notice, when we used the one that gave us y's, we had a dy out here, which is what we had to have. We need everything in terms of y. Can't mix x's and y's in here. So this gives us what we want, an expression in y. And the other one, to turn y equal x around, you just go x equal y, and so x is equal to y. The leftmost goes here. And now we can take this integral. This is the integral of -6 to 2. I'm just going to rewrite it again. Change the order slightly. -1/4 y squared minus y plus 3 dy. And then I need an antiderivative of y squared. So the -1/4 comes along. Antiderivative of y squared is y cubed over 3. And then the antiderivative of y is y squared over 2. Antiderivative of 3 is 3y. From -6 to 2. Equals. Now, I didn't do an estimate of this area because it's really big. But a big number like 20 or 30 would be fine. But a negative number or a number like 10,000, it's like not at all okay. So let's keep going here. I'm going to get, when I this becomes -1/12. When I substitute 2 in there, it's times 8. Minus, and when I substitute 2, I get 4 over 2, which is 2. When I substitute 2 in here, I get plus 6. Alright, so that's when I substituted 2. When I substitute -6, I'm going to get 6.
Mr. Shankin, can you put 4 instead of 2?
Oh, thank you. That's what I'm really good at. Okay. And then when I put 6 in here, I get -1/12 times 6 to the 3rd. And I'm pulling up my calculator. 6 to the 3rd is 216. It's actually -216. And then when I put in -6 into this one, I get 36 divided by 2 is 18, so it's -18. And when I put -6 in the last one, I get also a -18. And so, then I pull out my calculator and I get this result. A few of you can do the same thing as what I'm doing, and let's check each other's work. Okay, and I get this first part, I get 3 1/3. And then when I do the second part, I get -18. And so this becomes positive 21 1/3. That's the area between these two curves. And the practice quiz, you kind of asked, remember people asked for a little more practice on doing one of these sideways ones, and that's what we got right here. And the critical part of this, though, is to see that it doesn't have a consistent upper and lower function, only out to 2. From 2 to 3, it's got something else, so we needed to do this. Well, it really helped to do it this way. We could have done it the other way, but it would have just taken a lot longer. All right. So, let's go from here back to any questions on this before I go away from this though first. All right. no questions. Let's go back to one more question on the homework. I'll generally put more stuff in this in OneNotes than what we need. So I'm not going to get to everything in the OneNote, but I did cover everything I really needed to cover today. So, yeah, number 11. Suppose an object is moving along a line with velocity, it's a trig function. Find the distance traveled by the object in the time interval 0 to pi over 2. Alright, so in this first interval. And so this, on A, the distance traveled, we have to treat everything as it's a positive velocity. Well, everything is a positive velocity inside that because it's all above the t-axis. So I just need to do distance traveled in this case is the integral from 0 to pi over 2 of this function 3 sine of 2t dt. Technically we'd have absolute value around it, but the absolute value, everything is always positive in between this and this. So in order to do this integral, you can't do it directly. You have to do a u substitution because this is a function of t in here. U is 2t. du is 2 dt. du dt is equal to 2 and you multiply both sides by dt. Alright, so then dt is 1/2 du. So if these are t equals, so I'm going to rewrite this integral now, but I'm not going to use any t's, I'm going to use all u's. The 3 is going to come up front. This is going to be the sine of u instead of 2t. The dt is going to be replaced by 1/2 du. The 1/2 I'll just put out front. And then I'm going to change these to u's. So this ability to do u substitution is really important. We'll use it a lot throughout Calculus 2. So if you're rusty on this, you can go back to that section in Chapter 5 that does more of those problems. All right, when t is 0, you plug it in, u would also be 0. When t is pi over 2, plug it in, u becomes pi. Now the antiderivative, so 3/2 comes in. The antiderivative of sine of u is what's something whose derivative is sine? It's negative cosine of u. Because the derivative of cosine would be negative sine, so that's why we need the extra negative. Evaluated from 0 to pi, which is 3/2. When I substitute pi in there, I'm going to draw my little unit circle. Pi is way over here. Cosine is the x-coordinate of that point. So the cosine of pi is -1. The negative of the cosine of pi minus the negative of the cosine of 0. And cosine of pi is -1. Cosine of 0 is the x-coordinate of this point, which is 1. So what I'm going to get is equal to 3/2. Negative of a negative is +1. Negative of a negative is another +1. So the 2 cancels with the other 2, and I get 3. So that's the area underneath here. All right, we are out of time, and the homework today is 6.2. And I mentioned it earlier, I did remember to check with your group on number 32. Make sure that you're getting that correct. And we will stop here, and I will see you all on Wednesday. Any questions? Okay, have your spot check uploaded before class on Wednesday with at least 75% problems done.
I was
Stop the
wondering,
recording. Good. Yes.